As you increase the pressure of a gas above a liquid, it becomes more soluble. And we can compare that to liquids and solids. Pressure doesn't change the solubility of a liquid or a solid in a solvent. The solubility of a gas in a liquid is directly proportional to its pressure. So when you open up your soda, what do you notice? Or beer? It fizzes because you've lowered the pressure of carbon dioxide that's above the liquid. So that carbon dioxide starts to come out, becomes less soluble. It's known as Henry's law. We'll see that in a second here. Now, temperature of most solids generally increase in a hotter temperature of liquid. So here's the solubility of various salts in water. And for the most part, they all increase. And that's kind of convenient because you can dissolve up more solute in hot solvent. You can let it cool and it can crystallize out, and it can be a purification technique. And then I like to explain that it makes sense. You know, when you heat up butter, it melts, you give it kinetic energy, it overcomes the intermolecular forces that's holding it together. So these solids like sodium chloride or calcium chloride, a bunch of common salts here, when they're in a hotter liquid, it's easier for the crystal to fall apart due to that increased kinetic energy. So here is this Henry's law I just mentioned earlier. This states that the solubility of a gas in a liquid is proportional to the pressure over the solution. C is the molar concentration, pressure is the pressure, and K is a proportionality constant. And I've had physics teachers say it's a fudge factor. Put it in there, then you normally get a straight line, or it makes the equation work. All right, something new and exciting. Svante Arrhenius. You might have heard of the Arrhenius definition of an acid and base. Acids increase hydrogen ion concentration. Bases increase hydroxide concentration when added to water. And so he's kind of a famous guy. Lived from 1859 to 1927. And so it says here, originally a physicist, but often referred to as a chemist. He was one of the founders of the science of physical chemistry, and he won a Nobel Prize in 1903. But the interesting part of his life is before that, he noticed that, let's just talk about melting ice. You can go out and put sugar on the ice and it will melt for the same reasons salt does, but he noticed a lot of salts, like sodium chloride, would have double the colligative property effect. Like adding 1 mole of sugar would lower the vapor pressure, but adding 1 mole of sodium chloride would lower the vapor pressure by twice the amount. And he started to think about that, and he said, I have this theory. These ionic substances dissociate into their ions, and so you get more particles to disrupt the intermolecular forces. And it says here he was working on the conductivities of electrolytes, and he submitted a dissertation, and his committee of professors, they had never heard such a thing, and they weren't impressed, and they gave him the lowest passing grade. It says here he received 4th class degree, then they bumped it up to a 3rd. Later, he won a Nobel Prize for that work. So the point of this talk is when people make fun of your ideas, they're just validating them, perhaps. So here's our 3 colligative properties. We've looked at freezing point depression, boiling point elevation, osmotic pressure. But now we've thrown in a new little thing, this I. So we typically use this when we're dealing with electrolyte solutions. It's called the Van Hoff factor. And it counts for the fact that electrolytes dissociate. And the factor is the actual number of particles in solution after dissociation, number of formula units initially dissolved in solution. That is the Van Hoff factor. So what am I talking about? Well, here's this idea. You could put some sugar in water and it would lower its melting point. Put 1 mole in there. And you put 1 mole of C12H22O11 and you get 1 mole of this in solution. So one of these, 1 particle in solution. Now here's the sodium chloride. It dissociates into a sodium cation and chloride anion, and you get 2 particles dissolved. And here's something like sodium sulfate. It dissolves in water, and you're going to get 2 sodiums floating around, and 1 sulfate. That sums up to 3. So this would be the best salt to put on your frozen sidewalk.
Because it does triple the amount.
Right. You could use less. Now there might be practical amounts, things like what's cheapest, what's not as hard on the environment. So I think the city uses a lot of magnesium chloride and calcium chloride, not necessarily sodium chloride. We're all going to go brackish. The Van Hoff factor is usually smaller than predicted due to the formation of ion pairs. So here's sucrose. This is just for reference because it's not an electrolyte, but 1 to 1. And we should say this should dissociate into 2 things. It gets close, 1.9, and these are all 0.05 molar solutions. So why is that? And at very dilute solutions, we don't see this quite as big. So like a 0.00001, you're not going to see much ion pairing. What is an ion pair? It's made up of 1 or more cations and 1 or more anions held together by electrostatic forces. So think back to the beginning of this chapter when we had sodium chloride dissolving. All of this was surrounded by water. All of this was surrounded by water. And we said things were solvated and hydrated. And for the most part, all of them are that way, but there will be a few. I imagine they're partially solvated. This is what's called an ion pair. So this acts as 1 particle as far as a colligative property goes. A factor of 2, it's 1.9. We're kind of winding down the chapter. I'm just throwing in the exciting stuff here at the end. We need to talk about colloids. Sometimes we say we have a colloidal suspension. What is a colloidal suspension? A colloidal is a dispersion of particles in one substance throughout another. Colloidal particles are much larger than normal solute molecules. So here's a category of some colloidals: aerosols, foams, emulsions, gels. How many of you think you ingested a colloidal suspension today? Yeah, did you have any milk for breakfast? Yeah, so milk is a colloidal suspension. You have all this fat and proteins in there. There's this word that describes milk. I like to say it's opaque. What does that mean? Yeah, you can't see through it. And if you let your milk sit out, or it's just sit in the fridge forever, and you go to pour it out and you see all this clear liquid and then chunks of white, the colloidal suspension breaks. So a cloud is a colloidal suspension. See, right now, there's water vapor in this room. If I had a really cold glass and I set it down on the furniture, my wife would come by and ask me why I didn't put it on a coaster because of the condensation. But we can see through this room and we don't see any fog. Of course, when it gets colder and you go outside and you breathe out, there's all this moisture in your lungs, and immediately those water molecules start sticking together, and there's not enough of them that they form a drop or fall to the ground, but they form a colloidal suspension, and you see your breath. So this is a lunar laser. They shoot a laser on the moon. Somebody left a mirror up there. They can do various atmospheric measurement. And so there's dust. So here we see the Tynall effect. The laser's going up, and we can see it because it's getting scattered off of small particles of dirt. The Tynall effect is light scattering by particles in a colloid, such as very fine suspension. And it talks about something else here called Rayleigh scattering. in that the intensity of the scattered light is inversely proportional to the fourth power of the wavelength. So blue light is scattered more strongly than red light. So this explains why sunsets are red and the sky is blue. Because there's stuff up there, O2 molecules, N2 molecules, maybe some dirt, but a clear, pristine sky, there's only N2 molecules and O2 molecules. And the sun is putting out white light, goes across, and what gets scattered down is the blue. And so the sky appears blue. And then at sunset, the sunlight's coming straight over the horizon at your eye, and it's shining through all this atmosphere. And the blue light gets scattered out, and you perceive red light.